Another limit is 1 plus epsilon over 1 over epsilon goes to E, Napier's number. As epsilon goes to 0. So E is approximately 2.718 something something something. So for example, when fx is given by logarithmic function, the natural log, then fx plus delta minus fx is given by ln x plus delta minus ln x is given by x plus delta, which is given by 1 plus delta over x. So 1 over delta fx plus delta minus f over x is 1 over delta ln 1 plus delta over x, which can be written as 1 over x times delta over x ln 1 plus delta over x, right? So this is basically 1. You divide by x and then multiply by x is equal to x. And as delta goes to 0, 1 over x times delta goes to 0, delta over x, and then 1 plus delta over x, ln delta over x, 1 over x, ln 1 plus delta over x, delta over x. This is going to be E. So this is 1 over x. Therefore, dxt ln x is 1 over x. How about when fx is e to the x? Fx plus delta minus f over x is ex to the delta minus e to the x. E to the x, e to the delta minus e to the x. E to the x, e to the delta minus 1. Since by definition E is defined by 1 plus delta over 1 over delta, right? Therefore, e to the delta is 1 plus delta. E to the delta minus 1 is equal to delta. Therefore, fx plus delta minus f over x divided by delta is delta e to the x is e to the x. Another example, when f of x is given by a to the x, and we can write down, a as a is e to the ln a. You can prove this relation by taking the logarithm of a on both sides. Therefore, a to the x is e to the x ln a fx plus delta minus f of x is given by e to the x plus delta ln a minus e to the x ln a, which is e to the x ln a d delta ln a minus 1. Then e is 1 plus delta 1 over delta. Therefore, e to the delta ln a is or actually you can also write down e as 1 plus delta ln a 1 over delta ln a. Therefore, e to the delta ln a is 1 plus delta ln a. And delta over fx plus delta minus f over x is given by e to the ln a ln a, which is given by ax ln a. Inverse function. For example, y is sine inverse x. This is same as x equals sine y. We know that dy dx is now cosine y. From sine square y plus cosine square y is equal to 1. Cosine y is 1 minus sine square y 1/2. Therefore, dy dx is actually, it does a plus minus, but you can choose 1 minus sine y sine square y, which is 1 minus x square. So delta x delta y is 1 over delta y delta x is dy dx square root 1 minus x square over 1. Therefore, dy d sine inverse x is square root of 1 minus x square. Continue the discussion of the composite function. For example, composite function. For example, y is given by y gx. Then dx dy dg dy dx dg. This is called chain rule. Also, and y equal fx times gx. And this is dx dy is dx dfx gx plus fx dx dgx. You probably memorized it in high school days, but actually we can do this way. Y x plus delta minus y over x is given by fx plus delta gx plus delta minus fx gx, which is actually we can what you can do is we subtract this and add the same thing without changing anything, right? So I coined the term called do nothing, which is multiply by 1, add 0. Does not change, and it does not change mathematics. So we can do, in many cases, we can do the principles of do nothing. So yx plus delta minus yx divided by delta is delta over fx plus delta gx plus delta minus fx gx plus delta plus delta over fx gx plus delta minus fx gx. So we can write down as dx df g gf dx dg. So for example, yx is secant x, which is 1 over cosine x. So we can set gx as a cosine x, dg d1 over g is minus 1 over g squared, and dx dg is minus sine x. Therefore, dx secant x is minus 1 over g squared minus sine x, which is cosine square 1 times sine x. This is secant x tangent x. On the other hand, for y equal tangent x, which is sine x divided by cosine x, which is same as sine x secant x. Therefore, dx tangent x is dx sine x secant x plus sine x dx secant x. dx sine is cosine x secant x plus sine x, and dxt secant x is tangent x secant x, right? So that is 1 plus cosine square x sine square x is equal to secant square x. So interesting derivative, dxt secant x is secant x tangent x, dxt tangent x is secant square x. So it's interesting to see that dxt tangent x plus secant x is secant x tangent x plus secant square x is secant x tangent x plus secant x. So if we divide by, so this is a common term, this is common term. So if we divide by tangent x plus secant x on both sides, we get 1 over tangent x plus secant x dxt tangent x plus secant x is secant x is 1 over cosine x. Using this, we can define a logarithmic derivative. For example, dxt ln fx. So using chain rule, dft ln f dxt f of x is 1 over f dxt f of x. So that's a good example of a logarithmic derivative. That is 1 over tangent x plus secant x dxt tangent x plus secant x, which is dxt ln tangent x plus secant x is 1 over cosine x. So this logarithmic derivative is actually the basis of solve of differential equation. So differential equation is the definition is set of equations containing derivatives. So dy dx, sometimes y prime, this is first order derivative. Dx square, d square y, sometimes written as double prime, is second order derivative. Likewise, dxn, dny, we say y to the n is nth order derivative. On the other hand, nonlinear cases y prime square is second degree first order derivative. Y to the m's degree nth order derivative. But in this semester, we will be focusing on linear cases. We will be focusing on the linear derivative only, because nonlinear differential equation is hard to solve. So example, simple differential equation dx dy is 1 over cosine x. We know that dx d ln tangent x plus secant x is 1 over cosine x, right? Therefore, general solution y is given by logarithmic tangent x plus secant x plus some constant. Another case of logarithmic derivative is the following. Let's try dx d x plus square plus 1 plus 2 root x square plus 1 over 2x square root x square plus 1 x plus square root x square plus 1. Therefore, x plus square root x square plus 1 dx d x plus square root x square plus 1 is 1 over x square plus 1 is dx d ln x plus square root x square plus 1. So another very good example is dx dy is given by 1 over square root x square plus 1. Then we know that y is logarithmic function x plus square root x square plus 1 plus some constant. So let me try homework. Find 5 you can actually find logarithmic table by CRC, standard mathematical tables and formulas. You can Google it.
오늘 밤 서초구의 예상 기온은 20도이며 하늘이 흐리겠습니다.
continue the first order differential equation. Next chapter is the first order differential equation. We are considering linear case. For example, dx dy plus pxy is qx. This is standard form of the first order linear differential equation. The first step is transform this into dx d zx form. And we can try zx as some function times y over x. And we also set qx as qx is hx qx such that dx dzx is qx. More specifically, dx d hx yx is hx dx dyx dx dhx y is equal to hx qx. For non-zero hx, we obtain dx dyx plus hx over dx dhx y is equal to qx. But the original equation is such that, on the other hand, the original equation is dx dyx px yx is equal to qx. So if we compare with this equation and this equation, what do we get? This px should be the same as this, right? Therefore, px must be same as 1 over hx dx dhx dx d ln hx. Since qx are known function, given function, px, qx are given function. Therefore, number one, we first find hx such that dxt ln hx is px. And from dxt hxy is hx qx. So hxy is equal to hx prime qx prime dx prime plus some constant to c. Then solution is given by hx prime qx prime dx prime plus c. This example, dx dy plus cosine xy is equal to 0. That is, dxt ln hx is equal to 1 over cosine x. But we already found out this logarithmic derivative, right? We know that hx is tangent to x plus secant to x, right? Therefore, dxt hx yx is equal to 0, or hx yx is equal to c, as yx is given by some constant over tangent x plus secant x. Let me see. Another example. Dx dy plus secant xy equals tangent x. So the first step, dx dhx is ln hx is given by secant x. Therefore hx is tangent x plus secant x. Hx times tangent x is tangent x plus secant x times tangent x. Tangent square x plus secant x tangent x. And we apply the principle of doing nothing. that is 1 plus tangent square x minus 1 plus secant x tangent x. Which is same as dxt tangent x secant x minus x. dxt hx yx is same as hx qx, which is dxt tangent x plus secant x minus 1 is same as dxt tangent x secant x y. Therefore, the solution is given by tangent x plus secant x. Y is given by tangent x secant x minus 1 plus c. X, this is x. Therefore, yx is given by 1 plus c minus x tangent x plus secant x. Let's consider another example. dxt y plus y divided by 1 plus x squared equal to 0. So zx hx yx dxt ln hx is given by 1 over square root of x squared. So we already found that hx is given by x plus square root of x squared plus 1, or dxt x plus square root y is given by 0, or y is c divided by x plus x squared plus 1. Example, dxdy plus y over x squared plus 1 is given by x plus square root x squared plus 1. So step 1, dxt ln hx is 1 over square root of x squared plus 1. We know that hx is already given by x plus square root of x squared plus 1. Secondly, qx is hx qx is x plus square root x squared plus 1 times x plus square root x squared plus 1 is x. So dxt hxy is hx qx, q is x. Therefore, hxy is 1 over 2x squared plus 1, or y is x plus square root of x squared plus 1, 1/2 x squared plus c. we have found that the logarithmic derivative plays a very important role in the solution of first-order derivative. Few cases. So we already have one logarithmic derivative. First one, tangent x plus secant x. X plus x squared plus 1 cotangent x plus cs cx. So show that dxt ln cotangent x plus cs cx is minus cs cx. So this can be as homework. So perhaps let's stop here today and continue next week.